Assalamu alaikum students, welcome to a new lecture of Engineering Fluid Mechanics 2. In today's lecture we will continue with our topic of turbo machineries, and in the previous lecture we covered the basic energy considerations and we drew the velocity triangles, and we said that the absolute velocity V is equal to the sum of two velocities, that is the relative plus the blade velocity. So this is what we derived in the previous slide, and we also drew two triangles for the inlet and outlet sections, and then we said that what will be the velocity direction of the rotor and the force direction. If they are in the same direction, then the fan that we are talking about is that of a pump, but if they are in the opposite direction, then we are dealing with a turbine. So let's go into that again, and now let's talk about the forces and the moments involved, and then the torques that will be applied on the rotor by the shaft, and what will be their direction, and how will we differentiate between the pump and a turbine when it comes to the torques of the rotor that is being applied by the shaft. So again, this is the same scenario, and in this scenario we have a blade motion that is in this direction, and the velocity of the blade motion that is in this direction, and the force that the blade applies on this fluid. So these two are in the same direction, and we said that this scenario is for the pump where the energy is transmitted to the fluid. In the second scenario, we said that the blade direction is in this direction, and the blade velocity is in this direction, and the force that this blade applies on the fluid, the reaction force is in the opposite direction. So now what will happen when we take the force in terms of the torques? For example, if the force that this blade applies is multiplied by the, if we take this for example, if let's say that a certain amount of force is generated, like in this direction, if we like to draw it, if a force is generated and we take the perpendicular distance of this force from its axis of rotation, so then we are talking about torque. So if we are talking about torque, then what will happen if the direction in which the torque is generated is equal to is the same as the direction of the blade motion? So then that scenario will again be that of the pump, and the direction in which the torque is generated is opposite to the blade velocity direction. Then we will say that that is the direction, that is the scenario for the turbine. So now we will talk in terms of the torques and the power and the work that is done by the shaft on the rotor. So and we will also see in terms of the Reynolds transport theorem, we will apply our control volume and our control surfaces analysis on this turbines also, and we will talk about the conservation of angular momentum. Conservation of angular momentum in terms of the Reynolds transport theorem, and we will then see that how we are relating torques to these different velocities that we discussed in the previous lecture and now in this lecture. So now let's move forward. So this is what we discussed in the previous slide, that if we recall that the force times distance is torques, and or torques time the angular displacement. So work can be written as the force times distance or the torque times the angular displacement. So if the shaft torque, that is the shaft torque, the torque that the shaft applies to the rotor, and the rotor rotation of the shaft are in the same direction as we discussed previously, then the energy is transferred from the shaft to the rotor and from the rotor to the fluid, which is the scenario for the pump. So the machine is a pump, Then conversely, if the torque exerted by the shaft on the rotor is opposite to the direction of rotation, then we say that the energy is transferred, and it is transferred from the fluid to the rotor. So in that case, it is a turbine. So again, if we take that into the torque in terms of the work, so the amount of shaft torque and hence the amount of shaft work that is done by the shaft can be obtained from the moment of momentum equation that we derived previously in section 5.23, that is our conservation of angular momentum in terms of our Reynolds transport theorem. That these are the lectures that I recommended for you to go through again, so that you now understand that what we are talking about. It was for your revision only and not for evaluation purposes, just to be clear. So then this is what we get when we apply our conservation of angular momentum analysis to this scenario that we now have in terms of the work power and the forces that are involved now. So now we established in terms of the force and the blade motion that this will be for turbine, and this will be for a pump. And similarly, if the torque torque and the angular velocity of the rotor are in the same direction, then that scenario will be for a pump. But if the torque and the angular velocity of the rotor are in the opposite direction, then that scenario will be for the turbine. And similarly, it can also be said for the shaft work, the direction of the work, and so on. So far we have established this much. So now let's write an equation for the torques that are involved, and for that purpose we will go again to the continuum analysis that we established for our Reynolds transport theorem, and how our conservation of angular momentum can be applied to the control surface scenario that now we have. And if you recall this, if we put our extensive property as mv, then we will have a moment on the left hand side, that is the summation of the moment on the left hand side, that is the change in the system, overall system with respect to time, and that is the change in the control surfaces at the inlets and the outlets. That is what we meant by the controlled surfaces. So now we will look at the exchange of momentum across these controlled surfaces. So if we simplify it further, then on the left hand side we will get the torque, and on the right hand side we will have this term, that is the radius and the velocity that is involved in this case, and the rho VA will comes out to be the mass flow rate. So now let's look at it like this. And here the component of velocity that we are going to take is the axial component of velocity. As you remember that we have previously dealing with two components of velocity. One is the tangential component and the other is the axial component of the velocity. So it will be represented as the theta, and it will be represented as x. So here we are now taking the component of the velocity, that is the v theta. So the axial component of this equation applied to one-dimensional simplification of flow through a turbo machine rotor with section 1 as inlet and section 2 as outlet. So we have basically visualized two sections, that is one is section 1, the other is section 2. And if we apply this equation across these two sections, then we have our torque for the shaft at the in terms of our inlet and outlet. So these equations now can be written as the one for the inlet, that is m dot, this will come out to be m dot into r1 and v theta 1. So this is for our momentum that is being transferred in and the momentum that is being transferred out. So the contents that go in are represented as negative, and the constant contents that move out will be represented as positive. This is how our methodology is so far when we are treating the control surfaces, inlet and outlets. So now we have our equation for the torque. Now let's move forward and see it in terms of the work and the power that is involved. And one more thing to add, that is this note right here that we already discussed, that when shaft torque and rotation are in the same direction, we have a pump, and otherwise we have a turbine. Otherwise will be that the shaft torque and the rotation are not in the same direction, so that will be for the turbine. So now, as we established that the shaft, that is the shaft torque applied to contents of the control volume, the negative sign is associated with mass flow rate into the control volume, as we discussed previously, and positive is used with the outflow. So the sign of, we also have velocity and axial component of the velocity. So its sign depend on the blade motion, the direction of the blade motion. So the sign of the components depends on the direction of v theta and the blade motion. So if v theta and blades, the u, v theta and u is in the same direction, so v theta will be positive, and the sign of torque exerted by the shaft on the rotor will be positive. And if this is other way around, then the shaft torque will be is not in the same direction, then it will be negative otherwise. So then now let's move on and look at the shaft power, and this right here, the equation 12.2 that we discussed previously, that is this torque equation that we discussed previously. It is also known as the Euler turbo machine equation, and if we write it again, that is R cross V theta 1 and dot 1 at the inlet plus R V theta 2, that is R cross V theta 1 V theta 2 into m dot 2. So this is our Euler turbo machine equation. So now we can also relate this to work, because we know that the work is equal to torque multiplied by the angular velocity. So now the shaft power, sorry, that is the shaft power. So shaft power is related to shaft torque and the angular velocity. So if we multiply the shaft torque with angular velocity, then we can get another term, and that term combined with this equation and the equation that we previously derived, that is the Euler turbo machine equation. If we combine these two equations, we will have this equation right here for our shaft power. And now you can see that this equation is in terms of the two velocities that we are talking about. One is the blade motion, represents the blade motion, and the other is the absolute velocity, a component of the absolute velocity, that is the axial component of the absolute velocity, along with the mass in and mass out, mass flow rate in and mass flow rate out. Further, we can also write them in terms of the specific power, that is the power per unit mass flow rate, in terms of this, that in terms of the shaft work per unit mass. So if we take this per unit mass, this whole equation divided by m dot, then we get the shaft work that is involved in this scenario, and that shaft work can be obtained in terms of these two velocities as we discussed. And then again, as we already discussed, that v theta is positive when v theta and u are in the same direction, and negative otherwise. Also, we can now say for the power, that power is positive when shaft torque and this right here, the angular velocity, are in the same direction. So if T and W are in the same direction, then the power will be positive, and if it is not in the same direction, then the shaft power will be negative. Thus, shaft power is positive when power is supplied to the contents of the control volume. We are again establishing, adding to our initial statement, that when we are doing work on the system, that is our fluid, then it is scenario of the pump. So now we can see that in terms of the equation, that if W dot is positive and power is supplied to the contents of the control volume. So now we are back to that statement again, and negative otherwise if the fluid is working on the turbines on the shaft. So that is in the case for the turbine. So this outcome is consistent with the sign convention involving the work term in the energy equation considered in chapter 5, that is equation 5.67, the same section of our Reynolds transport theorem, in which we are talking about the first law of thermodynamics, and then we are talking about the powers and the works that are involved. So go through it also. Then if we take it as work per unit mass, so we will have shaft work, and that can be represented as in terms of these two velocities. One is the velocity of the rotor, and then the absolute velocity component, that is v theta 1 and v theta 2. Now taking the velocity triangle that we drew, that is in terms of the absolute velocity, the relative velocity, and the blade velocity, we can actually take the two components of our absolute velocity. One is along the tangential direction and one is along the axial direction, and we can say that this velocity, absolute velocity, has two components right here. One is the tangential component and the other is the axial component. So we can, if we have now two triangles, if we would like to draw it, we now have two triangles, and using these two triangles we can actually write some useful equations. So one is this bigger triangle right here, and if I draw that here, then this bigger triangle contains the absolute velocity v and its two components, vx and v theta, and this is, you see, a right angle triangle. So now we can actually apply our Pythagoras theorem, as we already know. So here v square is equal to v theta square plus vx square. So rearranging it like this, because we will use it somewhere else. Now we have another small triangle. If you would like to see right here, we have this small triangle also, and this is also a right angle triangle. So it contains W, Vx, and this small portion right here will be equal to, if we subtract V theta, sorry, if we subtract U from V theta. So this is what we get for this side. So now we have another right angle triangle, and writing equations for it, we can write it as such that by applying Pythagoras theorem to this small triangle, then we can say that W square is equal to Vx square plus V theta minus U whole square. So if I open this equation right here and simplify it by comparing these two equations, then I can write it in terms of this right here. So now you can see that we have an equation v theta u as v square u square and w square. These are the three velocities: our absolute velocity, our blade velocity, and our relative velocity. As we already discussed in the previous lecture, that how are these three velocities important, and we said that we are talking about the energy consideration in our previous chapter, in our previous slides, that is our previous lecture. But now we are talking about the momentum consideration. So now we are again back to these three velocities, that how are they related to the momentum and the power and the works that are involved. So based on the previous equation that we had, that was work done by the shaft, that was the W dot over m dot, and that was the power that is involved. So by combining this equation with 12.5 equation 12.5, and equation 12.5 was basically that of, if we write it in terms of the inlets and the outlets that are involved, that for equation 12.5, then the shaft work that we get is in terms of the difference of the absolute velocities at the outlet and the inlet, and the difference of the blade velocities at the outlet and the inlet, and the negative difference of the relative velocities at the outlet and the inlet divided by 2. So now you can see that we have our shaft work in terms of these three velocities that we discussed previously. So this is why they were crucial, and in the coming slides we will also be drawing velocity triangles, and we will again be using these three velocities again and again. So hope this was clear. So now let's have a look at this example, that is example 12.1 from your book. And this example is about the how that we will know that if you are dealing with a pump or a turbine. So the statement that is given is that the rotor shown in this figure right here rotates at a constant angular velocity that is given to us. Although the fluid initially approaches the rotor in axial direction, that is this right here, that the fluid approaches this rotor in the axial direction, the flow across the blades is primarily outwards. So the flow goes axial, but now it changes the direction, and then we have this inlet and outlet of this rotor. So it initially approaches this rotor in the axial direction, but then changes the direction. Now measurements indicate that the absolute velocity at the inlet and outlet are 12 meter per second and 15 meter per second, so respectively. So they are asking us that is this device a pump or a turbine. Note that this is our inlet right here, and this section is our outlet. So what we will have to do, we will take a section of this blade and we will start drawing our velocity triangles. So initially what we will have to assume is one thing, that the relative velocity that is the of the fluid is tangent to the blade profiles, and the velocity of the blade as it is moving in this direction right here, it will be in this direction. U1 and U2 will be in this direction correspondingly at both section 1 and section 2, that are the inlets and the outlets. So this is what our initial assumption is, and this is what they are stating it. And this is the rotor velocity at the inlet and the outlet calculated by using these two formulas. So with the known absolute velocity, fluid velocity, and the blade velocity at the inlet, we can draw the velocity triangle, the graphical representation of which is given right here. That is at the inlet and that is at the outlet. So the smaller radius right here is taken as the inlet, and the larger radius right here is taken as the outlet. So now we have assumed that the relative velocity is tangent to the blade profile, so both at the outlet and inlet, and we have our blade velocity that is in this direction at the outlet and at the inlet. So now we can add the third component, and it will be that of the absolute velocity, and from that we will know that if it is this study that we are doing, this case study is about a pump or a turbine. So this is how we will draw our two velocity triangles, both at the inlet and at the outlet. So now you can see this is our relative velocity, this is our blade velocity right here. We will add just one absolute velocity component, that is V1 right here. This is what is given. We have two components, the circumferential and the radial. So the absolute velocity right here is assumed to be radial at the inlet. Now at the outlet we will have our absolute velocity like this. So this is our velocity triangle at the outlet. So now you can see that this at the inlet, the absolute velocity had only one component, and that was in the radial direction, but at the outlet it now will have two components, both in the radial and in the circumferential direction. So this change in direction occurs in the direction in which the blades are moving. So the blades are moving in this direction, and the force that the blades apply will also be in this direction. So when these two directions are equal, the blade velocity direction and the force that these blades apply on the fluid that is encountering this rotor right here, then the particular scenario that we are dealing with is that of a pump. So this scenario right here is that of a pump. So what will be the scenario if we would like to take that as a turbine? So in that case, This will be our assumption. We will have our inlet at the larger radius and the outlet at the smaller radius. So now you can see with the same assumptions that the velocity is relative velocity is tangential at the inlet and the outlet, and the absolute velocity has the blade velocity is in this direction. As you can see, we can draw our velocity triangle, and now as you can see that the blade velocity is the rotor is moving in this direction, but the uh, velocity right here, has only one component, that is the circumferential, and at the outlet it now has both the radial and the circumferential components as well. So this will be the scenario for a turbine. This will be the scenario for a turbine in which the blade velocity is in this direction, u is in this direction, but the forces that will be applied, so to change the absolute velocity direction like this, it will be in the opposite direction. That will be the reaction of the blade. That will be the reaction force that is being applied on this blade, due to which the rotor is moving in this direction. So this is how we will differentiate, and the basis is this point right here, that the direction of the rotor velocity and the force that the rotor applies to change the direction of the absolute velocity from one component to two components. So this is how we will differentiate between a pump and a turbine.